It's a great pleasure to introduce our speaker today. Actually, this is really introducing somebody who's well known to an audience that mostly know him, but not everybody. So Martin is from the United Kingdom originally. He was educated in Britain. He completed his PhD in one of the earliest X-ray astronomy programs at at Leicester University in 1978. And he came to the Center for Astrophysics more or less right away. And he's made his career here. And it's actually been a very significant career, principally in X-ray astronomy, and within that, principally supermassive black holes and their manifestation as quasars. He's has about 400 publications to his credit, with a very large number of citations. But he's taken an interest in something closer by of late, as you can see from his title. And I have to say, this is the only introduction I can remember where any one of the following three words took part: love, fear, and greed. But anyway, we're here to hear from Martin Elvis on asteroids, how love, fear, and greed will determine our future in space and the future of astronomy. And I'm sure there are a lot of people who are very interested to know what the future holds. So Martin, the floor is yours.
Thank you, Charles, for a very nice introduction. Yes, I'm going to talk about asteroids and how I got into asteroids and what that means for astronomy. That means I'm going to have to leave out all sorts of very interesting things about ethics and law and of space exploration and expansion. But never mind, maybe you can ask me about that some other time when we, long from now, meet in the corridors or something. Okay, cool. Hang on. Okay, right. So I owe you an explanation really of how I moved from, or not moved completely, but changed my emphasis of my work from quasars to asteroids. Asteroids are pretty much the nearest thing you can study and still call it astronomy, I think. So, because I'm looking at near Earth asteroids. So the real starting point was my feeling that astronomy was in a crisis, because we got very used to having the great observatories, Hubble, Spitzer, and Chandra, for about 20 years, and having naturally assumed we're going to have access to that whole swath of electromagnetic spectrum forever. And that's just not true. But in those 20 years, it's become essential to doing astrophysics that we have this access. As the great band Nada Surf says, the stars are indifferent to astronomy. That is, they don't care about our technology. They radiate where they will, and we have to follow them. And we found out that that means following the entire spectrum for almost everything in astronomy. And these images show some of the examples where you can't understand what's going on if you just look at one of those bands. You need the whole thing. So we'd been, of course, hoping James Webb would be the first of a new generation, and I hope it is the first, to replacement more or less for Spitzer. The problem is that, of course, everybody knows it's cost about $10 billion. And at that rate, the NASA astrophysics budget can pay for about one flagship every 15 years, something like that. And Webb has a design lifetime of 5 years, which might be stretched to 10. It's limited by the fuel to stay on its orbit around L2. So it will be dead before there's a complementary mission at any other wavelength. So we could, of course, double or treble the budget and build several new flagships and get the simultaneity of coverage back again. But that does seem a little implausible at the moment. So I don't see a new generation of great observatories coming in if we stick to this $10 billion cost. It's just not going to happen. So the party's over unless we can drive these costs down. And you see, I've written about this in several places. So that's how I got into asteroids. Now it's quite obvious. I'll give you a little more detail as we go. So I'm going to talk about asteroids, and in order to frame this, I'm going to talk about why we should go to the asteroids, how we're going to go to the asteroids, the means, and the why now, the opportunity that's now with us if we can take it. So starting with motive. Starting with a quick background. Everybody knows this, I'm sure, but just in case, we're looking at these are asteroids, which are basically mountains flying in space, that mostly occupy the main belt of asteroids in orbits between the orbits of Mars and Jupiter. So planets not to scale there, of course. A few tens of thousands of the asteroids have been scattered into orbits that bring them into the inner solar system. Many of them come close to or cross the Earth's orbit, and those are called near-Earth objects. They're not near-Earth asteroids because there are a few dead comets mixed in there, and we don't know which is which straight off. And asteroids originate from the breakup of the planetesimals that started forming in the solar system. They have diameters of about 1,000 kilometers or several hundred kilometers anyway. And they get hot from radioactive decay early in the history of the solar system and melt. And so as they melt, they differentiate. The silicon rock crystallizes out and lets the iron, however, it doesn't do that. It moves further to the center. So it falls to the core and makes it a solid metal core after time when it's cooled, surrounded by a large silicate mantle. And on the outside, or if the asteroid didn't get too hot, there's some untouched material, or maybe the smaller planetesimals just don't get hot enough and retain this original material, which is full of organic molecules and water and other goodies. And then these planetesimals broke up through collisions, high-speed collisions, and that led to the creation of asteroids, which tend to be either carbonaceous, silicate, or metallic, as they come from one of these three regions. Of course, that's oversimplified, but that's where we are. Okay, so what are the motives? Love, fear, and greed. And let's take each of those in turn. What do we mean by being motivated by these three great forces that explain so much of human behavior? Well, I'm going to cheat, of course. In the case of love, I'm really talking about love of knowledge, curiosity. And what I point out here is that asteroids are involved in at least four big questions that I think are quite important. I don't think, these are very well known within the field, the asteroid field, but I don't think they get out too much to the rest of science. So let's talk about asteroids and the history of the solar system. There's a thing called the NEISS model, which was came out in 2005 in 3 simultaneous papers in Nature. I'd never heard of such a thing before. And it used planetesimals to change the orbits of the gas giants, because as the gas giants scatter these planetesimals around, they are also in turn affected by that and gradually move the orbits of the gas giants until Saturn and Jupiter become into resonance. And then great things happen. And you lead to a heavy scattering of asteroids as the Jupiter and Saturn then move and cause much more scattering of asteroids into the inner solar system, bombarding Mars, the Earth, and the Moon. And this is called the late heavy bombardment. This is all happening after the gas disk of the protoplanetary nebula has dissipated. Some of those get captured as Trojans and irregular moons around the gas giants. Some get thrown outwards and may create the Kuiper belt. And that's the concept behind this model. So how would you know if this is right? Well, there's lots of tests. There's lots of questions about this model. It's been updated. But basically, the objects that still have information about this time are the asteroids. Planets have changed too much. So we can test solar system history by using the asteroids. I should point out that I am not an asteroid scientist really, or a planetary scientist. I've moved into a sort of adjacent field, which so I don't claim to know the great details about these different topics. Another one is we live on this ocean-covered planet. And where does that ocean come from? Since the Earth was molten, it's unlikely water was retained in that time, and it had to be brought in from somewhere else. And that late bombardment we talked about could be the source of the water that was brought to Earth. This will be sometime after the collision that created the moon. The oceans aren't actually that much water on a solar system scale. It's 1% of the mass of the Earth. And putting it in that context of asteroids, it's about 5 times the amount of water in the biggest asteroid series. So it's plausible that a handful of water-bearing planetesimals did hit the Earth and could provide the water from Earth. The way people are looking at testing this is with the deuterium to hydrogen ratio, which appears to be much more like that. The Earth's oceans deuterium to hydrogen ratio is much more like that of the asteroids than of comets, for instance. This is a result from the Rosetta mission, which gave a very nice accurate measurement here, way above the Earth's ratio. There's also a connection with the origin of life, and I'm sure this is well known to our Origin of Life initiative people, but that same late bombardment could well have brought prebiotic molecules along with the water and may have sped up or enabled the origin of life on Earth. Meteorites are known to contain a lot of complex molecules, organic molecules, amino acids, sugars, and even more complex ones. I think the record breaker is this one here, which has 1,000 or so atoms in it. This is work done across the street in Oxford Street from our molecular and cellular biology folks. And what they're measuring is meteorites, which are the few percent of hard material that survived that's descent into the atmosphere. There may well be far more complex materials in the delicate material that was lost on entry. So it could be that there's actually a lot more interesting materials in the asteroids than we know about yet. So the obvious thing is go and look, find out what, go to some asteroids and find out what they're made of, what composition they have. And of course, this is starting already with Hayabusa 2 and OSIRIS-REx, which have both landed and gathered samples from asteroids, from carbonaceous asteroids in particular, where the highest chance of getting these organics is coming from. So that's a question for our extrasolar planet friends. The last question is crucial to having this technological civilization. You must have iron to build something large. I think this is a true statement. It'd be interesting to discuss. But that's a problem because iron, as in the planetesimals, sinks very efficiently to the core of a molten body like the Earth used to be, carrying with it a lot of precious metals, the siderophiles, which dissolve in liquid iron. So that leaves the question of why we have iron in the Earth's crust at all. And so the idea that has been given some evidence for, at least, is that asteroids brought iron to the Earth during the late Vernier, which is actually the tail end of the original accretion of material onto the Earth, rather than this late bombardment. It happens earlier. Okay, if that's enough reason to take the asteroids seriously as scientific objects of study, what about fear? Well, I think this is one that's very well known. This is a nice MPC, Minor Planet Center, Earth-centric coordinates that's showing the known asteroids zipping by the Earth. We're basically in a kind of shooting gallery. And we all know that the a giant asteroid about 65 million years ago killed the dinosaurs, and there's nothing about our current situation that suggests that can't happen again. Killing of the dinosaurs is strangely selected. I'll let you think about that for a while. Among all the threats to humankind's existence, this is the only one that we can definitely prevent, because we know how to do it in principle. And already the surveys have found 90% of potential dinosaur killers that kill 1 kilometer or bigger in diameter. That's good, but it's not good enough because we only need one to kill us all off. And there's 100 yet left to find. So we really need to find the rest of them so that we can be sure that this isn't a problem, or if there is a problem, deal with it. Perhaps more directly scary is the idea of a 20-meter sized asteroid like the one that fell on Chelyabinsk or near to Chelyabinsk. City killer scale. The Tunguska 1908 impact flattened forest over an area the size of Metro DC area. And so that's why it gets the term city killer. It can destroy a complete metropolitan area. These come by every so many decades. There are 4 noted there. I would worry if I was Russian. The universe may actually be out to get you. And then greed. How do we motivate? Greed is easy to be motivated by. Many people spend their whole lives being motivated that way. And there have been these statements repeated by many famous folks that the first trillionaire will be an asteroid miner. So I got started when people started saying this. I found myself being skeptical and wanting to put in the numbers. So you'll see some of that result in a moment. The answer was maybe. What would they mine? Well, those precious metals, platinum, palladium, and so on, are worth a large amount. Water and iron, possibly. Water and iron, of course, are not worth much on the ground, on Earth, but in orbit, they can be worth quite a lot. Let's see. Platinum actually sells at $50 million a ton. So that's an easy case. Water and iron in space, it costs of order $1.5 million per ton to get them there. And you can't just unpack them. You have to have the spacecraft around them, et cetera, et cetera. So it probably could well be $3 million a ton in practice. And so you could make quite a bit from selling water and iron to other folks in space. But the problem is there's no one to hear you selling. In space, no one can hear you sell because there's no economy in space, with no customers. Okay, that's the motivation. Let's think about the means. How would we go about doing any of these things, investigating asteroids? So finding the asteroids turns out to be something that's pretty well in hand, I would say. There are 2 big surveys coming up over the next 10 years. Finding asteroids by reflected sunlight is what the optical telescope, the Rubin Observatory, is going to do in its legacy survey of space and time. And they expect to find 3/4 of the ones that are pretty big, 100 meters or so across or more. They'll also get the colors for these. And that's good because that identifies the stony ones, because there's an absorption feature in the red that's due to silicate rocks, olivine and pyroxene. That survey is going to take about 10 years. Well, it will take 10 years. The other method, of course, instead of reflection, is the emission from the black body of these objects. Because they are about the same distance from the sun as the Earth, they have about the same temperature. That means they glow very brightly at around 10 microns. And so that's what the Near-Earth Object Surveyor, of which Amy Mainzer is the lead scientist, at least, is going to do. And that's going to find 90% of the ones bigger than 140 meters across. And because you know the distance and you know the brightness, you know the black body area, so you can get out the size quite accurately for these objects. So you begin to learn quite a bit. And if you can put those 2 together, you can get the reflectivity, the albedo of these objects. And if they're very dark, then they're going to be very likely carbonaceous. So we start to learn a surprising amount from these objects alone. So by early 2030s, we'll have a huge catalog of near-Earth objects that we could visit in principle, or mine, or avoid, deflect. How would we study the asteroids? Well, right now, there's actually a lot of enthusiasm for sending spacecraft there. I mentioned Hayabusa 2 and OSIRIS-REx already. In 9 days' time, Lucy will be launched to go to the Trojans and start investigating their origin and whether it fits, for instance, with the NEAS model. And next year, the Psyche mission will go to Psyche, which is bound to cause lots of confusion. So I put in 16 Psyche as its full name. And that Psyche is the largest and best candidate for being a solid iron core remnant from a planetesimal. So we're going to visit the interior of an object that melted for the first time. It's a complete new type of object, a strange new world. Okay, how would we deal with fear? Instead, can we stop an asteroid hitting us? There are several ways. A gravity tractor is the most reliable one, because you can't turn off gravity. You just go to one in front or behind the asteroid and pull on it with a large mass and keep that mass away from the asteroid. More directly, you could just hit it with a bigger, most fast-moving and massive object you can put together. And there's actually already going to be a test of this. The DART mission will launch in November, just announced the launch date, and it's going to intercept with, in about a year after that, it's going to intercept and hit the moon of a little asteroid called Didymos and change its orbit, so that you can measure the momentum transfer from the input from the DART vehicle to the asteroid and see how much you can actually change the orbit of an asteroid. This will be the first time humanity has deliberately changed the orbit of anything in the solar system. So it's kind of momentous in a sense. It's a very small change, but it is a deliberate one. Going up in the scale, you could also go the Bruce Willis route and fire a nuke and explode a nuke right near the surface, or preferably a little below the surface of an asteroid. This is being studied at Los Alamos, no surprise, I suppose, but they seem to be, they've done good work that suggests this is a good approach. There are problems with all of these approaches, though. The gravity tractor probably needs about 20 years warning, and we may not have that much time. There's a workaround, but it's not guaranteed, and you need a guarantee. Kinetic impactors probably need several of the largest rockets we have, launching the biggest mass we can put up in order to make sure that the asteroid does not hit the Earth. And you need multiple hits that all work. The new Starship may change that number usefully, but we'll see. And both the kinetic impactor and the nukes may shatter the asteroid instead of slowing it down. And depending on the size of the product, we may still suffer some danger from that. This is a picture of a meteorite being shattered by a 6 km/s bullet fired at the vertical test stand at Ames. So clearly we need to experiment and do so safely on asteroids that will never hit the Earth, however badly we mess up. And that's going to take a lot of practice to get this right and find the optimum methods. And now greed. Now, if we're going to find valuable materials that we can sell to someone, we first need to do the prospecting. So you can do that remotely, but it's quite hard. You'd like to say, look at for the strongest water feature, which is at about 3 microns, and that's a terrible location from the ground because it's in the atmospheric gap between the K and the L bands. And by the time you get to the L band, you can see in this plot, you do see this absorption feature, which is due to water or OH bonds. And but the sky is very bright there. So it's only been done for a few very bright, large, nearby asteroids. And we'd like to do a lot more. And so the obvious thing to do is to launch a space telescope. It doesn't have to be that big, and it could easily cover that range. In fact, the ESA's aerial M-class mission does cover that range quite nicely and would be a great choice, except it can't track moving objects, so it won't actually do the job. I've talked to the PI about this, and it's just not changeable. So maybe NASA should follow on with the NEO Surveyor with another mission to do this. Or since this is about greed and commercial opportunities, maybe a private enterprise would decide to do this, and in order to profit off the intellectual property of knowing which asteroids are good for mining for water. And an example might be this Twinkle satellite that's a commercial exoplanet mission. They believe. I guess they are going to build a much cheaper satellite than aerial, and enough cheaper that they can sell time and make a profit, observing time and make a profit. So once you've done that, how would you mine the asteroids? Well, it's not easy. Platinum is very rich in some asteroids. 30 grams per ton, however, is all you get. That's richer than mines on Earth for platinum, but it's still not easy. It's very hard to mine, it's energy intensive, and you have to do all this mining robotically and at the original orbit, in the original orbit of the asteroid. Because if you bring back raw material, you're throwing away a vast fraction of it just to get the platinum, and that's a terribly wasteful thing to do. So that's not easy. Water's much easier because it comes at like 100 kilograms per ton, and it's pretty easy to mine. You just have to heat up the rock and drive off the water, which is held in clays and things like that, mostly, we believe, and then capture that water. And that's the most plausible thing. But iron, actually, if you really wanted iron instead of platinum, you could bring it's about pure iron, nickel iron, some of these objects. Just a segment of the core. So you just slice out of the asteroid the whatever size and shape you can cope with and bring it back. So that would actually be the easiest way, easiest thing to do. And in principle, the water and iron might undercut Earth, water and iron, particularly in a high orbit like geostationary orbit, where the energetics are much more in favor of the asteroid water than the water supplied from the ground. And maybe in low Earth orbit too, which is where you really want to make a profit, because that's, as you'll see, where most of the action will be for the next decade or two. And still, one has to say, what is the market? Who are the customers going to be? So we'll get to that in a moment. Here's a point about the value of intellectual property of knowing which asteroids contain the water. If you look at all the known asteroids, only 3%, roughly a quarter of the carbonaceous asteroids are likely to be rich in water. There's another estimate saying 6%. It has a factor of 2 uncertainty on it, so maybe we're not in disagreement, but it's in that range. And that's of the known asteroids, but of the ones we could get to, the situation is much worse. As of now, we can actually get to, with a 1-ton payload, which is not very much, just 3% of all the known near-Earth asteroids. So that's 3% of 3% are the actually valuable ones. So knowing which one that is going to be very important. And this is where I started criticizing or critiquing the asteroid mining companies back in 2014. And I put together this equation, which is obviously a ripoff of the Drake equation, and simplified even. And I was very pleased because New Scientist called it the Elvis equation. I thought, this is great. But I think they're the only people who ever called it the Elvis equation. But, you know, it's something. It's something. So clearly, knowing where the water is valuable intellectual property, and maybe that's enough to start a business. And then you've got to prospect and mine the asteroids. First, you've got to prospect them with in situ probes to prove the ore reserve, ore body, as they call it. If you have a 25% chance, a 1 in 4 chance of getting, and you know if something is carbonaceous, and then it's 1 in 4 chance of it being water rich, then simple exercise in binomial probability tells you need about 10 probes. This was a project from an undergraduate, Thomas Esty, back in 2013. And we published that. And because you need many probes, they have to be cheap, they have to be autonomous, they'll probably be small. And then you have problems that need solving, how you're going to, what the propulsion will be, the communications back to Earth, and the navigation. And all of those have potential solutions that are being worked on. And so I think this is a promising field that soon will have real results. So maybe in the 2030s, there'll be the first asteroid mining expeditions to try and, if we can find customers, sell material to people in orbit or to operations in orbit. And we've just realized that this is rare and valuable real estate, like beachfront property. That means it's going to lead to a number of extra legal activities, let's say. And so I've started working with Tony Milligan and Alana Krolikovsky, who are ethicists and policy person. And we've written about this. So to dramatize it, there's espionage, claim jumping, rustling, and piracy, all are quite possible. And the interesting thing is that under the Outer Space Treaty, which is pretty much all the space law that really is, these go from being pretty much encouraged by, in the case of spying and espionage, to definitely legal. You cannot own an asteroid and have any mineral rights on it as yet, to very likely legal. Rustling an asteroid would mean putting a rocket on it and changing its orbit so that you can find it, but the person who did all the prospecting could not. Piracy, at least, is totally illegal. You cannot go to somebody's spacecraft on its way back full of ore and steal the ore, because the spacecraft is very definitely their property still. So the problem is that we're looking at law in a vacuum. There's no case studies for this, and there's no body that adjudicates disputes, and that's going to cause a lot of trouble. And that's where Tony and Alana and I have been writing about this at some length. It applies to the moon too, by the way, which we've also written about. So that's how you would go about doing these things, the means, and now finally the opportunity. Basically, why now? And of course, that's because this new so-called new space movement is cutting the cost of doing business in space. Most famously, SpaceX has reduced the cost of launching a ton to orbit by about a factor 5. That's to low Earth orbit. And they're aiming with Starship to lower it by another factor 5. So we're talking at order of magnitude reduction in launch costs since the last decadal survey, basically. Also, on-orbit refueling is a real thing now. It's been done by Northrop with their mission extension vehicle. And now Orbit Fab has come up with a standardized valve to allow this to be fitted to many satellites and many suppliers of fuel. And they seem to be going great guns. This is good. And there's also an in-space economy starting up in low Earth orbit, doing many other things, which I'll show you on the next slide. Just to repeat, those mineral resources are worth 0 until you have a customer. But there are customers. We've already seen suborbital and orbital tourism. There's actually a film crew now on the International Space Station from Russia, filming movies there. Tom Cruise intends to film a movie there too. And those people may not like, eventually the rich tourists who do that may not like the Spartan conditions that they have to endure in the International Space Station. Then there's research. This is ongoing in materials science, cold atoms, genomics, medicine, and a private space station would be far more efficient than the International Space Station if the scientists could themselves go to orbit and do the work, which is obviously becoming possible with the arrival of the Dragon and soon we hope the Boeing Starliner. Here's an example of research that could be game-changing in medicine. TechShot is a company, and they are hoping to build 3D print human organs. This can now be done for simple organs like the liver. You can build ears on a frame, but more complex organs, like a heart, for instance, it's very difficult to print in Earth gravity because cells just sort of sink down and form a blob instead of staying in where you want them to. In zero gravity or microgravity, that's not the case. And so TechShot is hoping to prove that you can build more complex structures out of cells, human cells, in orbit. That could become quite an industry manufacturing industry. More immediately, manufacturing industry, more immediate use of manufacturing in space would be optical fibers. These fluoride CBLAN fibers that are shown on the left here, they should be able to transmit 10 times the bandwidth of the optical fibers we use today. And obviously there's an infinite need for the internet to grow, to send all those cat videos around. And also the problem with ZBLAN is if you make it in Earth gravity, little crystals form, as in the picture on the right. But if you got a test long ago, actually, by people at Marshall Space Flight Center, showed that in a parabolic flight, you could extrude these in zero gravity, and the crystals do not form. This was just maybe tens of centimeters that they were able to do in a 30-second flight, 30-second weightlessness period. Now there are 3 companies working on the International Space Station to try and turn that eventually from tens of centimeters to kilometers. And once you can make kilometers of this material, it's worth millions of dollars per kilogram. And so the cost of sending it to space and bringing back the finished product and actually manufacturing it there can be quite trivial compared with the amount of money you can get for it. And that points to if that works, they will need a lot of space to produce significant amounts of this material. And that points to the advent of commercial space stations. There will be one by 2030. Axiom Space is going to attach a module to the International Space Station in 2025, and they have a contract for that. And they will gradually add modules until they have enough to be an independent space station. And around 2030, they plan on detaching from the International Space Station and offering all the above tourism, research, and manufacturing possibilities to customers on a purely commercial basis. So those people working in space, those activities taking place in space will need resources, and that could be customers for asteroidal materials, space resources. So that's why 2030s for asteroid mining beginning is a plausible possibility. And of course, it'll be small scale at first. But once it is profitable, then it will just grow exponentially the way economies do, so long as there is demand. And the space activity will not be limited to what a government program can fund anymore. It will be funded by profit, and it will progress relatively rapidly, I would bet. What this will do is expand our capabilities of doing things in space, which are pretty darn limited right now, and lower the cost of doing them. I thought it'd be nice to see how maybe CFA could contribute to the asteroid work. And of course, we've already started. There was an X-ray imaging spectrometer called REXIS on OSIRIS-REx, mainly built at MIT, but with a lot of work from the Josh Grindley's group, including heroic efforts by Brandon Allen at the last minute, really, almost, to make it work. We've been using Magellan, the PISCO instrument, Tony Stark's instrument, to get refined orbits and colors of asteroids that are promising targets. What I really like is a kind of X-shooter on one of the Magellans, where you could get an instant simultaneous spectrum from the optical through the near infrared at least. It would be great for following up the characterization of the asteroids coming from these 2 surveys I mentioned, but also, of course, for the other transients, particularly those coming from the Rubin telescope survey. It may need changes in the way we run Magellan. Let's not go there. Another contribution we could make to asteroid, and in fact planetary research in general, is an X-ray mirror and detector package, the Suzanne Romains optics, and the CMOS detectors being developed by Ralph Kraft and Almus Kenter. Together, they make a light and compact and radiation hard package that would be very well suited to planetary missions. And J-Sub Hong has studied some of these for the moon, for instance. And they'd be just as good for prospecting asteroids for resources, as well as the science of asteroids. And the great advantage that they have over other possible missions, instruments, is that they make for a practical way to do X-ray navigation using millisecond pulsars, which means you can get 3D positions of and velocities out of these measurements, good to a few kilometers, it seems, from a test done on the ISS. And lastly, why not build our own infrared spectroscopy mission, or propose an infrared spectroscopy mission for small body research? This could be like Josh Grindley's plan for looking at the infrared emission from very high redshift gamma ray bursts. And maybe we have another scientific case for this. It could allow us to propose the same mission to different places in NASA or elsewhere, and get a lot of great science done, and even improve the prospects for asteroid mining, as I've been talking about. So I think if this actually does get going, and we have to remain some skeptical, what would happen is that the profits, the commercial activities would help us allay our fear of being destroyed by a killer asteroid. Because there are three problems. I've mentioned the need to practice deflection techniques, and low cost would make it much easier to do that in numbers. But the other one is that if we now found a asteroid on a collision course for Earth, we probably don't have enough lead time to start building a mission and then launch it, because that takes at least 5 years. But if there were many more launches taking place, which seems very highly likely now, then this could have a kind of priority over any commercial venture. Could we bump it off its slot, and we could fly a satellite quicker? We wouldn't have to wait for that. But better still, we could get down to almost zero wait time if we use the low cost to put several deflectors on orbit, for instance, at the Earth-Moon Lagrange point, not first Lagrange point, and then they'd be ready to go as soon as we discover an incoming asteroid that is a threat. And finally, because we can get higher mass with these new rockets coming along, we could use that to get higher delta V in the target asteroid by putting in more propellant, moving at higher speed. Could also just have a bigger mass object, but half mv squared suggests higher velocity might be the way to go. And these advantages for deflecting killer asteroids would also have gains for planetary science, because the same spacecraft could be cheaper, and we could have more capable planetary missions, allowing a much larger rate of planetary missions. Right now, there's 1 or 2 per year, 15 per decade, roughly. Maybe we could get up to 10 times that with small, carefully chosen and missions, making use of these savings. Even better, the same idea of storing a mission at the L1 point is that we could have target of opportunity interception missions to comets, and of course, even more excitingly, to interstellar objects as they swing by. And those will be starting to be discovered, what, 1 a year with LSST, something like that is the estimate. Okay, and then what about astrophysics? That was all planetary science. Because of the high mass at low cost, because the spacecraft assembly, manufacturing, refueling on orbit, all is going to happen pretty soon. Larger margins on the spacecraft can be afforded. That cuts the design cost. More power leads to cheaper electronics. And being able to assemble in orbit means it's easier to design to survive the rigors of launch. So in astronomy, radio, on-orbit assembly means we can manufacture bigger antennae than we were used to thinking about. We can avoid the origami-like folding for telescopes in the far infrared through UV. X-ray telescopes can use the full diameter of the Starship, and that would require a longer focal length, but we're assembling in orbit now, so that's not a problem. Gamma ray makes use of the mass and size allowances that are much more generous than we're used to. But best of all, I think it means that interferometers in space can become a normal thing, and that is where the biggest advance, I suspect, might be. And that's how I got from quasars to asteroids, by trying to see what was best for astrophysics in the future. Thank you.
Okay, thank you very much, Martin. It's a very interesting evolution from X-ray astronomy to asteroids. I would actually mention, if I may, the probably the most active contribution right now to asteroid science is done by the Minor Planet Center, which is
yes, of course.
wholly at the CFA under the leadership of Matt Payne. But anyway, the talk is open for questions. Questions can be put into the chat, or can people raise their hand?
Gary has, I don't know.
Gary's got his hands. Gary, go ahead.
Okay, very thought-provoking talk, Martin, very enjoyable. Question though is, from the economic standpoint, what is the argument for asteroids over using the growing infrastructure related to working on the moon?
No, that's quite right. I concentrated on asteroids, but I've also been looking at the moon and its resources. The moon has advantages in that it's always in the same place, more or less, and it's only 3 days away, and you can teleoperate there fairly easily. So I think it could well be that the moon is the first place that we'll start to use resources from space. Eventually, the resources of the asteroids are far larger, so we probably would end up going there. But yeah, I totally agree.
Thanks.
Okay, so Joe, you're up.
Hi, very nice talk, Martin. I was wondering if you could outline a plausible scenario by which, in the near term that this mining could take place. So say, for example, you wanted to get a ton of water from an asteroid to somewhere around the Earth orbit. Mm-hmm. How would you do that, efficiently and more cheaply than just sending up multiple rockets from the ground?
Right. So the question is whether you can find a water-bearing asteroid that's worth. So there are two approaches. I've concentrated on saying, well, we need to find an asteroid that contains at least, $1 billion worth of water to bring back, because otherwise venture capitalists are not going to be interested. So there are not very many of those. And that's what my little equation was about. We need to find them first, and that's what the surveys will achieve. They have to be a very low delta V, so we can actually move a lot of material around. But an alternative approach suggested by Joel Sercel of Transastra is to look at very small asteroids, maybe 5 to 10 meters across. They might contain a few hundred, $100 million worth of water, but because they're easy to catch and you already very near the Earth, it may be cheaper to do it that way, and that's fine. I don't mind which way it's done, but his big problem is finding the things, because they're so tiny that they're very, very faint and be very hard to see with ground-based telescopes. He thinks he's going to do this by a version of shift and add. You choose it's called synthetic tracking, and you take the same picture several times and you say, well, if the asteroid had this orbit, it would be here, and if there. So you basically can get a much deeper image for given orbits, and maybe that will work. He's very optimistic. I still am a bit skeptical.
Okay, I'll interject a question, if I may. So you mentioned the Roman, the LSST survey for near-Earth objects, and the NEO surveyor, and they're quite complementary, which is always a plus. But one thing I'm not clear on in my head is, in terms of just discovery potential, to what extent does it really add value to the discovery numbers to have both of them, or are they really, in some sense, substantially redundant in terms of discovery potential?
Well, I think they give you different information is the first thing, and the bias of the optical against dark asteroids, and when we say dark, we're talking about a few percent reflectivity. So they're darker than fresh asphalt. That's a bias in all current surveys except for Neowise that needs to be taken away. And we may find there are very many more carbonaceous asteroids than we had thought. So that would be a significant change. On the other hand, it's much cheaper to do it with LSST, I think. No, I guess not, because LSST is $1 billion project, and the Near-Earth Object Surveyor is a $500 million project. So they're actually fairly comparable in cost. But you get different information, and when you and both of them will be going down deeper into the in magnitude than we've ever gone before for these surveys. Most surveys for asteroids use 1.5 meter telescopes. So it's a big difference going to an effectively a 6.5 meter. So that you'll go down the size curve, the log N, log B curve, and somewhere it turns up. It's fairly flat, but somewhere it turns up, and that will be new information. And which kind of asteroids do that, and it's going to be a lot of changes, I suspect, in our understanding of the asteroid population.
Okay, so are there any other questions? I don't see anything in the chat. Well, I'll take advantage of the opportunity to ask one more. You were talking about the commercial development, much of which would be in low Earth orbit. Is actually orbit crowding becoming a problem with some of these plans, because the number of spacecraft is growing rapidly already?
Yes, evidently that's a sort of different issue, but if you can't get to low Earth orbit because there's too many of these satellites in the way, then of course the whole thing collapses as a concept, and so many other things are not possible. So this is a problem that will have to get solved regardless. The orbital debris problem is right at a critical point, I think, now that we have thousands of satellites instead of a few hundred, and going to be many more. So that has to be solved to make any of this possible. There is a lot of work going on that, but it's going to need legislation, I think, and also international agreements.
Yeah, absolutely.
Beyond what I do. So
yeah. Okay, well, I think I don't see any more hands raised. So let's actually thank Martin again for a visionary talk and for the exploitation of love, fear, and greed in an astronomy colloquium, I think, is quite extraordinary. So thank you very much, Martin. And
thank you. A pleasure.
And looking forward to a brilliant future when LSST and NEO Surveyor get going.
Indeed.
Right. Okay. Bye-bye, everybody.